Okay, so welcome to E126. This is our first online discussion. Uh, this week should be your final exam week, but instead of giving you your final exams, I'll try to give you some discussions for the last part of our course syllabus, and maybe next week will be your exam. It will be a series of exam, all the other topics and finals, and if uh, we can also add your midterms next week, then good. So this discussion will be about chapter. We have chapter 4 already. We finished chapter 3 before, and chapter 3 is about electric field and Coulomb's law. So chapter 4 is about electric flux density. Electric flux density. So before we discuss what's electric flux density, first we discuss what is electric flux. So before, there's a uh, famous scientist, physicist named Michael Faraday that experimented with charges. Then he observed if we have a charge positively charged here, uh, he observed that there are lines that are going outward from that charge. And we already did this one in chapter 3. We solved the electric field that also in that direction. And now, there's another, they try to quantify these lines that are coming from this charge. And that lines, actually, they call it the electric flux. Electric flux. And the symbol we will be using for electric flux, we will be using the psi symbol. And according to Faraday, the number of lines that going out when he put a spherical metal around the charge, then he observed the electric flux that goes outward. Then he says that electric flux, every line of electric flux, uh, uh, or every coulomb of charge, this is Q, every coulomb of this charge generate one line going outward. So what does this mean? This means that according to him that the total electric flux should be equal to the total charge of the charge. So this is according to Faraday. So therefore, if the electric flux is equal to Q, then the unit for electric flux is also in coulomb. And from the previous discussion in chapter 3, we tried to incorporate charges in our electric field, and we define them in different ways. For example, we have this one, rho b. What is this rho b? This is the volume density of a charge, and rho v is a density, so it's the volume divided by, or the charge. I should say the charge, the total charge divided by the total volume. dV. And the unit for this one is coulomb per cubic meter. We also have other types. We have for the surface area, dq over dA, and for a straight line or lines, line charge density, dq over dl. And this dv, dA, and dl, uh, this was also discussed. How do we solve, or what is dv, what is dA, what's dl? If you remember, it depends on the coordinate system that you will be using. So for example, if we use a rectangular coordinate system, then dv is actually dx, dy, and dz times dz. We already discussed this one, and you can review them from the previous discussions. We also summarize this one. We put it in table, and the, we can use them as our references. So now, we can solve for electric flux by using this concept. So from rho b, from the if the volume charge density is given, usually volume charge density, then we can, if we try to solve for the uh, charge, dq now will be equal to cross multiply rho v times the differential volume. So if you want to solve for q is just equal to, we need to integrate both sides. So the integral of rho v times dv, if this is a volume integral. And therefore, this is also equal to, if you want to solve for the electric flux, we can use this formula to solve for the total electric flux. And this is also true with other given, if the given is surface charge density or line charge density. So we can just change this one into the integral of rho dv surface area rho s, or it's not dv, it should be dA, or d rho l dl. This is a line integral. So that's how to solve for the electric flux or the charge, total charge. Let's take an example using that one. So example 1. So if we have here a problem, says find the charge in a volume defined by uh, 1 less than or equal to r up to 2 meters in spherical coordinate system. If the volume charge density is equal to this equation 5, so it's not a constant, it's a varying volume charge density, cosine squared p all over r to the 4th. So the unit for this one is coulomb per cubic meter. So this is in spherical coordinate system. So we want to solve for the total volume defined by this one. So how do we solve that one? We can use the formula that we derived on the top here. So the net charge now, Q, will be equal to the integral volume rho v dv. And this is in spherical coordinate system. So what will be our dv in spherical coordinate system? So if you look at your table, dv for spherical coordinate system is actually equal to r squared sine theta dr d theta times d phi. So this is the differential volume. So we're given with the volume charge density, and we know the differential volume, so we can now solve for this one. So it will be equal to, so this will be a triple integration because we have a triple differential in the differential volume, and rho b will be equal to 5 cosine squared phi all over r raised to 4. And we multiply this one with the differential volume, which is equal to r squared sine theta dr d theta times d phi. Now, what will be our limit? Our limit will depend on the differentials. So for first for the dr, so for dr, our limit is in the given. We want to determine from r equals 1 to 2. So this will be from 1 to 2 meters. For the theta, we will be using from 0. So that's 1 revolution. So it should be 0 to 2 pi. And for phi, it's from, we don't need 1 revolution. We only need the half of the sphere from 0 to pi. Then we will rotate that one into 1 revolution. So this will be our limit, and we will solve this one. This is a triple integration. So simplify first. Triple integral. We can cancel out r squared here. So we have r squared at the bottom, and we have cosine squared times that one. So 5 cosine squared phi sine theta all over r squared dr d theta d phi. So from 1 to 0 to 2 pi and 0 to pi. Then solving the integral now, we can just solve this one manually, each of the integral. So we can first solve for dr. We want to first solve for dr. So other components here, phi and theta, should be a constant. So we can put them outside the integral of so this 0 to 2 pi and 0 to pi. So we can take out the other values, sine theta, and also d theta and d phi. Then we do from 1 to 2 of 1 over r squared dr. So what's the integral of 1 over r squared? So the integral of 1 over r squared, this is the same as r raised to negative 2 dr. So using general power rule, integral of this one, n plus 1. So r negative 2 plus 1 divided by negative 2 plus 1. So this is r raised to negative 1 all over negative 1, or negative 1 over r. So it will be negative 1 over r. Then, okay, let's copy 0 to 2 pi, 0 to pi, 5 cosine squared, phi sine theta, d theta d phi. So the answer is negative 1 over r, and this is from 1 to 2. and we can apply upper limit minus lower limit. So this whole thing now, this one will be equal to negative 1 over upper limit negative 1 over 2 minus the lower limit minus minus, so 1 over 1, which is equal to 1 minus 1 half, or this is equal to 1 half. So if we go back here, this will be equal to, we can now take out that 1 half from 0 to 2 by 0 to pi 5 cosine squared phi sine theta d theta d phi. So we're done with the first one. So next, we can integrate now the limit from 0 to pi. And what's that one? That will be theta. Phi is from 0 to 2 pi. So if we do that, 1 half 0 to 2 pi, then I put here, this is d phi. Then inside is, so sine theta or cosine squared, we can take that one, cosine squared phi. Then there's a 5 here. Then the integral of sine theta d theta from 0 to pi. So to evaluate this one, what will be the integral of sine theta? So this part here will be equal to, the integral of sine theta is negative cosine theta, and the limit is from 0 to pi. So upper limit minus lower limit, so negative cosine of pi plus cosine pi. What is cosine of pi? And cosine of pi is equal to negative 1, and this one is also negative 1. So the answer here will be equal to sorry, there's a mistake here. This should be 0. The lower limit is 0, so it should be 0. It's not negative 1. It should be positive 1. Cosine of 0 is positive 1. So we have negative 1 plus 1. Negative 1 plus 1 is positive 2. So the answer there will be positive 2. And if you multiply it with 1 half, then it will cancel out. So 1 half times 2. 1 half is the integral of r dr, while 2 is the integral for d cosine theta. And the only remaining integral now will be from 0 to 2 pi 5 cosine squared phi d phi. And how do we integrate this one? It's cosine squared. So we can use identity here. What is cosine squared? Theta. So cosine squared theta, using an identity, this is equal to 1 plus cosine 2x all over 2. Cosine 2 theta over 2. So this is an identity, trigonometric identity. So instead of integrating cosine squared, we can integrate this one. So what will be the integral of this one? Just kidding. So the integral of this one, cosine squared d theta. So the integral of cosine squared d theta will be the same as the integral of 1 half plus 1/2 cosine 2 theta d theta. So the integral will be equal to integral of 1/2 d theta is 1/2 theta. Then plus the integral of cosine 2 theta is sine 2 theta times 1/2, the neutralizing factor. So 1/2 times 1/2 is 1/4 sine of 2 theta. So this will be our integral, but there's a limit from 0 to 2 pi. So from 0 to 2, then we can now apply upper limit minus lower limit. So upper limit, we can just put it here. I'll try to solve this one here, this point. So upper limit 1/2 times 2 pi plus 1/4 sine of 2 times 2 pi. Then the lower limit minus 1/2 times 0 plus 1/4 sine of 0. So this is 0. This is also 0. Sine of 0 is 0. Sine of 2 times 2 pi, sine of 4 pi is also equal to 0. And cancel out, cancel out. So the answer here will be just equal to pi. So we can now substitute this one to the problem. So Q now. So what will be our Q? Our Q, this will cancel out, and this is equal to pi. This one is equal to pi, and there's also pi there. So the answer will be 5 pi. And the unit for this one is coulomb. So 5 pi coulomb. So that's the total net charge. Net charge from 1 to 2 radius with a varying volume charge density. So, okay. Next, so that's electric flux. Now, the topic for this chapter is actually not electric flux, it's flux density. So what will be electric flux density? What do you know about electric flux density? So this is a density, electric flux density. And the symbol for this one will be letter D. This is a vector. Remember, electric flux density is a vector. Electric flux is a scalar quantity, but electric flux density is a vector. So, what is electric flux density? Mathematically, electric flux density is a density. So, this is a surface area density. It's similar with the surface charge density because charge is in coulomb, and this one electric flux is also in coulomb. But instead of dq, we will be using electric flux d psi all over the surface area. And this time I will be using ds to represent a surface area. And it's a vector, and it has a direction. And what does that direction? The direction is actually the direction of the surface area. And remember before, how do we make a surface area a vector? So we discussed before that the direction is always perpendicular to the surface area. So for example, this is area of a charge density. Then you get here a very small differential area, ds. Then the direction will be perpendicular. This will be A. The direction of the electric flux density is the same direction as that surface area. So now, we know that uh, the electric flux density is just the ratio of the electric flux and the surface area. So if we try to solve the electric flux here, d phi d psi will be equal to d, it's a vector, times ds. And remember, we said that ds can also be a vector. So in general, we do this one as a dot product if we make this one as a vector. And the direction of that vector is in the this direction here, perpendicular to the surface area. So this is in general, a differential electric flux is the dot product between the flux density and the surface area. So now with the experiment of Michael Faraday, he uses a sphere as a surface area. So if you have a charge here plus Q, then there's a sphere here and there's another sphere. This is an experiment of Michael Faraday. Then he computed for the electric flux density at the different region of this one. The first one is the inner sphere. So what will be the electric flux density at the inner sphere? And what will be the electric flux density at the outer sphere? So what he did is he calculated the electric flux density from so first for the inner sphere. So if the radius of the inner sphere, so if this one r equals a and the outer sphere is r equals b. So he computed for the first one for r equals a. So if r equals a, then he found out that because phi or psi is equal to, remember, psi is just equal to the net charge inside the sphere. So to solve for d, density is flux divided by the area. So the total flux will be equal to Q because that's our psi, and we divide it with the total surface area. And what will be the total surface area? It will be the total surface area of the sphere, of the inner sphere. So what's the formula for the surface area of a sphere? It is, for a sphere, area of a sphere, surface area, this is equal to 4 pi r squared. So for the inner sphere, the electric flux density now will be equal to Q divided by 4 pi, instead of r squared, r is equal to a, so this is a squared. And the direction, if we put this one in spherical coordinate system, is just in the radial direction, outward. So that's the electric flux density at r equals in a, or in the inner sphere. For the outer sphere, r equals b, the answer is